So the second part, that is calculation of tractive effort Ft. In that Ft, the second part is due to the tractive effort to overcome the train resistance, that is Fr, to overcome the train resistance, that is Fr. So the tractive effort has been used or is been useful for that to afford the total resistance of that locomotive to overcome that motion of that locomotive. That means it has been used, the tractive effort has been used because for the locomotive to overcome that total resistance offered by the locomotive to the motion of the train. That means when the locomotive is running in linear motion or angular acceleration or rotational way, linear way or rotational way or angular way, but that the total weight of the locomotive is also plays a crucial role, because the total weight because the resistance offered by the locomotive to the motion of the train is also crucial, very important. So the total amount of force developed at the axle of the wheel has been sufficient for the locomotive to go further and to reach a destination with all the total resistance offered by itself to the motion of that train, that is itself. The train is itself, right? So if you see that the tractive effort to overcome the train resistance, that is Fr, is nothing but, in order to see that the particular derivation part, you will see that let R is the resistance or the train resistance in Newton per ton, and you know that tractive effort to overcome the total resistance of the train, Fr, because here the resistance has been offered by the locomotive on the track, and that air resistance or the wind resistance, because it has to overcome that wind. If it is the locomotive is traveling in opposite to the direction of the wind, then it has to overcome the wind direction. So it has that sufficient resistance on that level track, and also it has to overcome that resistance to that flow of wind. So if you based upon that, the tractive effort to overcome the resistance Fr is nothing but W, that is weight of the train, right, or dead weight, it is measured in tons, multiplied by R, that is the train resistance in Newton per tons. Train resistance Newton per tons. So if you see that the units is newtons, the units is newtons. As we know that W, the weight of the train, that is in tons, and its units is Newton per tons. So ton cancel and resultant Newton is that unit for this Fr, that is tractive effort to overcome the train resistance, right? So next you will see that what is the tractive effort to overcome the gravitational force, So the third factor in calculation of the tractive effort is Ft. So here if you see that in the tractive effort to overcome the gravitational force or pull, that is Fg. So as we discussed that the tractive effort is nothing but the force experienced by the traction motors at the axle of the wheel in order to overcome that angular and rotational acceleration, the first factor, and the second one is to overcome that train resistance, and the third one is that amount of force required in order to overcome the gravitational pull or force. So in the third one, in order to overcome the gravitational pull or force, first we will see that this is the ground, this part is the ground, and in which the track, this is the track, has been elevated with an angle theta from the ground, and if you see that this is then locomotive or train, and the direction of the train is upwards, that means away to the gravitational force, If you see that the train is moving in the upward direction, so if you see that if you resolve the component here, that is here one is that W, this one is the W, and this is that elevation angle, that is theta. So this component will be represented as or resolved as W cos theta, right, and this component as W sin theta. So if you see that the W cos theta is perpendicular to the train motion, if you see that the W cos component, the W cos theta component is perpendicular to the motion of the train, to the motion of the train. So the W cos theta, the cos theta component is acting perpendicular to the train motion. If you see that W sin theta, it is acting opposite direction to the train. So it is acting opposite direction to the train motion, to the train motion. So now the total tractive or the effort tractive force required in order to overcome this gravitational force which has been given by Fg or pull, it has been given by Fg. So before deriving that expression for Fg, we will see that theta is equal to inclination of the gradient. Theta is nothing but inclination of the gradient, and W is that weight of the train, that is in tons. And now that tractive effort to overcome the gravitational force can be given as Fg equal to 1000 into W multiplied by 9.81 into sine theta, into 9.81 into sine theta, because it has to overcome this gravitational force, because by resolving that component there, W sine theta is acting opposite to the direction of the train, where W cos theta is acting perpendicular to the train motion. So where the W cos theta is acting perpendicular to the train motion, the train may not have that much, or should means it itself will not, that W cos theta is not opposing to the motion of that train, it is just acting perpendicular. But W sin theta is been acting opposite to the direction of the train. So that is the reason, in order to overcome that total gravitational force, the Fg is nothing but 1000 into W multiplied by 9.81 into sine theta, multiplied by 9.81 into sine theta, that is nothing but W into sine theta. This is a total force required for tractive force required in order to overcome the gravitational pull, that is Fg, right? So, and units are newtons. If you see that normally what will happen, if you see that in the gradient in an electric traction system, if you see the gradient, what it has been distance of the train to that, how much amount of meters it has been upward, that is 1 meter or 100 meters. Again I am repeating, based upon that gradient, how we are defining this electric Indian rail system, based upon the length of the rail to how much distance or the meters, that is 1 meter or 100 meters, it has been projecting. So similarly here also the gradient, the G is nothing but the percentage gradient G, where it has been getting that, where the G is been obtained as, we know that the sine theta is nothing but elevation, that is nothing but elevation, that is the gradient part divided by distance along the track, distance along the entire track. So what we are now, the elevation is nothing but a G, what is the gradient, what we discussed, and that how much distance, for example 1 meter or 100 meters, here I have chosen 100 meters. So now that elevation, the sine theta, this sine theta can be obtained as G by 100, can be obtained as G by 100, right? So now when you substitute that this sine theta value in this expression, the sine theta in this expression, now resultant force or the resultant tractive effort required to overcome the gravitational force, that is Fg, can be derived as, or can be obtained as Fg equivalent to 100 into W multiplied by 9.81 into, instead of this sine theta you substitute G by 100, in the sense of sine theta you substitute G by 100. So how much now we are getting? We are getting 98.1 Wg newtons, Wg newtons. So this is the tractive effort to overcome the gravitational pull. The gravitational pull or force is nothing but because see here sin theta is been replaced by g by 100, right? This 100 and this 100 I am going to cancel this, so 10 multiplied by 9.81 nothing but 98.1 into W into g, and units are newtons. Units are newtons. This is a tractive effort to overcome the gravitational pull or force. Fg is equal to 98.1 into W into g, that is newtons. That is newtons. Done. So the resultant tractive effort in order to overcome that acceleration, that is linear or rotational acceleration, the first one, that is Fa, and the tractive force to overcome the train resistance, that is Fr, and the tractive effort to overcome the gravitational force or pull, that is plus or minus Fg. So if you see that what we discussed or what we derived in that just now, that is Fa is nothing but 277.8 into We, right, into alpha, that is acceleration, that is kilometer per hour per second, plus W into R, that is that tractive effort to overcome the train resistance, plus or minus the tractive effort to overcome the gravitational force, that is 98.1 into W into G, and the total units are newtons, and the total units are newtons. So this is the total tractive effort to overcome that angular or linear or rotational acceleration, train resistance, and the gravitational pull or force, right? So the train has to have the sufficient tractive force in order to have the motion on its level track, So next we are going to discuss about the power calculation. So the next concept is power output from the driving wheel. So in this derivation, we'll first see what are the terms used here. The first thing is that let Ft is nothing but the tractive effort. First tractive effort Ft, that is in units are in newtons. Nextly V, that is the speed, that is meter per second. Next is power is the power output, that is watts or kilowatts. Now we know that power output is nothing but rate of doing work, that is P is equal to work done by time. It is nothing but speed into distance. Work done is nothing but speed into distance divided by time, where it can be written as speed into or work done is nothing but force into distance. Work done is nothing but force into distance. Right? Force into distance is nothing but work done. So the work done is nothing but force into distance by time. Now what we can write? We can represent it as force multiplied by distance by time, speed. Force multiplied by force into distance by time is speed. So that P is equal to, or P output is nothing but force, that is nothing but Ft, that is tractive force, multiplied by speed, that is V, and units are watts. Right? So if you see that if the V is in watt, V is in meter per second. If suppose it is kilometer per second. If it is kilometer per second, then what is the power output? Power out is nothing but P into Ft into V divided by 3600 into kilowatt. Right. So this is the power output from the driving wheel. Again I'll repeat that in order to see the derivation of the power output from the driving wheel, first we'll see that the tractive effort, that is Ft, that units are in Newton, and V is that speed, that is meter per second, and next P is that power output, that is in watts or kilowatts. Now rated output power is nothing but work power. Rate of doing work is nothing but work, that is nothing but work done by time. So work done is nothing but force into distance divided by time. So the force into distance by time nothing but speed. And the force is nothing but the tractive effort, that is Ft, and multiplied by V, that is the speed. And if suppose that here the V speed is in meter per second, if it is that is kilometer per second, then how can we represent? We can represent that P is equal to the power delivered from that driving wheel, that is P output nothing but Ft by 3600 into V into, that is units are kilowatts. The units are kilowatts. This is an expression of power for power output from that during the power output from the driving wheel, that is P is equal to Ft into V by 3600 into, and units are kilowatts. Units are kilowatts.